This is your presenter Asloob Mudassar, and I am presenting slide number 61 of the course on laser physics. Question is, discuss gain saturation for homogeneous line absorption for the case of a 4-level laser system when the saturating electromagnetic wave is a light pulse of intensity I as a function of time. The answer is, if the pulse duration is very long compared to the lifetime tau, we can neglect rate of change of population in level 3, that is dn3 over dt, compared to the spontaneous decay term n3 over tau in equation number 60.1, and we obtain the same result as given in equation number 60.5, that is n3 is equal to n30 divided by 1 plus I of t divided by is, where I of t is the intensity of the saturating beam, is is the saturation intensity. So let me explain this formula given in let me explain this equation given in equation number 61.1 using equation from the appendix. You see that this is the dn3 over dt is actually the rate equation for level number 3 in a 4-level system, where level 2 decays spontaneously, level 4 and level 4 decays spontaneously, decays with rapidly, not spontaneously but very rapidly, and the leasing levels were the level number 3 and the level number 2. So we have written the decay rate equation for the level number 3. So dn3 over dt is equal to rp is the pump rate minus w times n3, which is the stimulated emission term, because the negative sign means that it will try to decrease the population in the level number 3, and then we have a minus n3 over tau, which is the spontaneous emission term. So in the present case, when the period of the saturating beam is very long in comparison with the lifetime of that level, that is tau, so the length of the period, so the length of the pulse is very long in comparison with the tau, which means that tau is very small in comparison with the saturating beam. So the term n3 over tau, which is the spontaneously emitted term, is a very dominant term. The saturating beam will try to increase the population of the level 3, whereas at the same time the population will decay through the spontaneous emission process very quickly. So the term which is n3 over tau, that is the spontaneously emitted term, will dominate and the population of n3 will stay the same. So under that condition, and you see that this is what we are considering under the saturation condition. So under that condition, the population of L3 will approximately be the same, and the rate of change of the population of N3 with respect to time will be 0. So dn3 over dt is equal to 0, and this will give you, if you solve this equation under this condition, that the rate of n3 with respect to time is 0, then you can get n3 is equal to rp into tau over 1 plus omega into tau. So this is what we have explained over here, that is, we have obtained n3 in this formula. But you know that in the appendix we have discussed the beam which was continuous beam, and here we are considering a pulse, and for that pulse we are using I as a constant, as a function of time. So n3 is equal to n30 over 1 plus I of t, that is I as a function of time, divided by the saturation intensity. So this I of t is actually the intensity of the saturating beam, and the same gain coefficient as given in equation number 60.6, which is reproduced over here, that is G is equal to G0 over 1 plus I of t divided by Is. In equation number 60.6 we used only I over Is, because there I was a continuous beam and not as a function of time. But here, since we are using a pulse, so the formula will be modified, that I will be represented by I as a function of time. So G is equal to G0 divided by 1 plus I of t divided by Is, as given in equation number 61.2. So how we transformed from equation number 1 to equation number 2, this is also explained in the appendix. So you see that once we have solved this equation, that is we have obtained N3 is equal to Rp tau over 1 plus omega 1 plus W into tau, where W is the transition rate of the stimulated process and Rp is the pumping rate. The intensity, we have obtained this relation earlier, that is intensity is given by W into h nu divided by sigma, where sigma is the absorption cross section of the material, especially for the level number 3, and the saturation intensity was equal to h nu over sigma into tau. The ratio of these two intensities, that is I over Is, is equal to omega into tau. So introducing these parameters and also introducing N30 is equal to Rp tau, we obtain the results, that is N3 is equal to N30 over 1 plus 1 plus I over Is. So this is what I have explained. But you see that if you introduced these two parameters, that is the gain coefficient sigma is equal to G is the gain coefficient. If you introduced G, the gain coefficient is equal to sigma times N3, because the population of N2 is 0 in this case. In a 4-level system, the population of level N2 stays 0, stays approximately 0. So we have G, that is the gain coefficient, is equal to sigma times N3. And introducing G naught is equal to sigma times N30, substituting these two, introducing these two variables, that is introducing N3 over here in the formula of G is equal to sigma times N3, introducing N3 from equation number 60.5 over here, and introducing G naught is equal to sigma times N30, we obtain the result, that is G is equal to G naught over 1 plus I over Is. But you know that for the case of a pulse, this I will be represented by I of t, and this G naught is actually given by 2 pi square over 3 n epsilon naught Ch multiplied by the absolute square of mu multiplied by N30 multiplied by nu prime and then multiplied by G of nu prime minus nu naught. So having explained these terms, the gain coefficient in case of the saturating beam as a pulse having a pulse duration much longer as compared with the lifetime of the level number 3, we have obtained the gain coefficient as given in equation number 2, that is G is equal to G naught over 1 plus I of t divided by Is. So I of t over here is again the intensity of the saturating beam as a function of time, and Is is the saturation intensity. So this is what we have addressed the case of the pulse having long duration time compared with the lifetime tau of the level number 3. And you see that we have found the same formula as we have found for the case of the continuous beam. So the gain coefficient in both cases is the same, except that the I in that case will be replaced by I of t. Now we are going to discuss another case. Now if the light pulse is very short compared with the spontaneous lifetime tau, then during the interaction of the light pulse with the material, the pump rate Rp and the spontaneous decay rate N3 over tau can be neglected compared to the stimulated term Wn3, and the differential equation number in 60.1 takes the form, that is dN3 over dt is equal to minus W times N3. So here we have neglected the two terms, that is the Rp term, that is the pump rate term, and the spontaneously emission term, which is N3 over tau. Let's look at the appendix again. So you see that this was the rate equation. Now we are using a pulse of very short pulse duration, much shorter in comparison with the lifetime of the level 3, which is tau. So under that condition, what will happen? The population of N3 will increase, which will only be compensated by the stimulated emission term Wn3. And due to very strong pulse, the Rp, which is the pump rate, and the spontaneous emission term, which is N3 over tau, they can be safely ignored in comparison with the stimulated emission term, which is W times N3. So we can simply write in case of a short pulse duration that dn3 over dt is equal to minus omega times n3. For example, in this case, that is in case of the light pulse with very short duration, we can write from the rate equation that dn3 over dt is equal to minus w times n3, where w is the stimulated emission transition rate. And substituting the value of w, we have a minus sigma I over h nu multiplied by n3. And we can also write this equivalently, that I over h nu over sigma. This h nu over sigma can be replaced by gamma s. So we have final result as dn over the dn3 over dt is equal to minus I over gamma s multiplied by n3, where gamma s is equal to h nu over sigma is the saturation energy in fluence. And you know that the fluence means that the energy absorbed by the material per unit area from the pulse is called fluence. So we have gamma s is equal to h nu over sigma is the saturation energy fluence of a 4-level laser system, and is twice the saturation fluence for an absorber which has a value equal to h nu over 2 sigma. So here in this case, for a 4-level signal, the value of the saturation energy fluence is twice that of the absorber. So we have a gamma s is equal to h nu over sigma. The last equation can be written as, so we have dn3 over n3 is equal to minus 1 over gamma s, and then we have I dt. So integrating over long period of time, because we have a pulse over here, so we have the integral on both sides of this one, that is the integral of dn3 over n3 is equal to minus 1 over gamma s, and then the integral of I of t into dt. So solving this integral and then obtaining the value of n3 as a function of time, we have n3 as a function of time is equal to n30 multiplied by e to the power minus gamma of t over gamma s, where we have introduced n30 is equal to rp times tau, where rp is the pump rate and tau is the spontaneous lifetime or the lifetime of the level number 3. So n30 is the population of level 3 before the arrival of the pulse. That's why we have written is 0 with this one, because it is before the arrival of the pulse. The saturated gain coefficient will be G is equal to G naught e to the power minus gamma of t over gamma s, where we have used G naught is equal to sigma times n30, and this is the unsaturated gain coefficient, and follows from equation number 60.7 as, because from the equation number 60.7 the unsaturated gain coefficient was defined as given in 61.5. So G naught is equal to 2 pi square over 3 n epsilon naught ch multiplied by the absolute square of mu multiplied by n30 multiplied by nu prime and multiplied by g of nu prime minus nu naught. That is the shape of the gain line function. You see that this is the gain in the case when the pulse duration was very short. The gain coefficient is given by G, which is G is equal to G naught e to the power minus gamma of t over gamma s. So this e to the power of this function, that is the exponential function, is a decaying function. But the mean profile is determined by the function G naught. And we have found that G naught is over here as given in equation number 61.5. So G naught has the same shape as in case of the as in the previous case, that is the shape of the gain line remains unchanged for the pulse regime when saturation occurs. So in case of saturation occurs, the shape of the gain line will be the same as we used for the continuous case. So even for the pulse case having short duration, the shape of the gain line would remain the same, and is given by G naught is equal to this on the right hand side of equation number 61.5. So we have explained all the questions, that is we have calculated the gain coefficient when the pulse duration is very short as given in equation number 61.4, and when the pulse duration is longer in comparison with the lifetime of the level 3, then we have G is equal to G naught over 1 plus I of t over Is. And you see that in both cases we find that these formulas are very close, not very close, that is equation number 61.2 is the same as obtained for the case of continuous beam. But only the difference is that there we have I as a constant, but here in this formula we have I as a function of time. So this is the difference. But you know that here this formula in case of short pulse the result is different, but you see that this G naught will help us to say that the shape of the gain line remains unchanged for the pulse regime when saturation occurs. So this is the end of slide number 61.